Welcome back. Today, we're diving straight into a truly fascinating explainer where we trace the entire life cycle of essential oils. We're going to follow the chemical engineering journey step by step, from the raw plant material pulled straight out of the earth all the way to highly purified, isolated molecules in the lab. If you're curious about the hidden engineering behind the scents we interact with every single day, you're definitely in the right place. So, to kick things off, let's start with a really foundational question. What exactly gives a plant its essence? I mean, think about it. What creates that powerful, unmistakable scent when you crush a mint leaf between your fingers, or when you peel a fresh orange? What is the invisible chemistry happening right there inside those everyday plants? Well, it all comes down to essential oils. By definition, these are hydrophobic, volatile organic compounds obtained from plant material. Now, volatile simply means they evaporate easily into the air, and that's exactly why they reach our noses so fast and register as those beautiful fragrances. They literally contain the fundamental essence of the plant. Chemically speaking, the foundation of all these scents relies on the isoprene rule. Discovered back in the late 19th century, this rule shows us that these complex scents are built from nature's very own molecular Lego blocks, these simple repeating units called isoprene. It's just an incredibly elegant system. Here's our roadmap for this explainer. First, the nature of essential oils, followed by extracting the raw essence, separating complex chemical mixtures, advanced molecular distillation, and finally, mapping the chemical fingerprint. Let's keep moving. Step 1. Extracting the raw essence, getting the oil. Traditionally, the industry has leaned heavily on steam distillation. You boil water, pass that steam right through the crushed plant material, and catch the vapor. But there's a pretty massive drawback here. That high heat brings a huge risk of thermal degradation. It can literally cook and destroy the fragile odor-producing compounds, especially those delicate esters, which leaves you with an inferior, kind of burnt perfume profile. But on the flip side, we have cutting-edge methods now, like supercritical CO2 extraction. This technique uses immense hydrostatic pressure and supercritical fluids to pull the essential oil out of the plant at very low temperatures. You get high-purity yields and absolutely zero damaging heat. The data on this is striking, especially when we compare extraction methods for basil leaves. The highly desired aromatic compounds, the oxygenated monoterpenes, almost double when using supercritical fluid extraction, coming in at 11.7%. Traditional hydrodistillation, it sits way down at 6.1%. By skipping the boiling water, the supercritical method yields nearly double the high-value aromatic molecules. It's a real game changer. Moving to step 2, separating complex chemical mixtures, refining the oil. Now that we have the raw, unrefined oil, we have to separate it. This is basically a massive thermodynamic puzzle. And to show you exactly how it's solved, we're going to walk through a complete, real-world lab experiment presented by Dr. Chem on separating essential oil components. The lab setup relies on fractional vacuum distillation. It has an evaporator at the bottom and a packed column right in the middle. By applying a vacuum at the very top of the column, Dr. Chem drastically lowers the boiling point of the oil. This incredibly clever trick allows the lab to use the slight differences in vapor pressure between various molecules to separate them. The lighter, more volatile compounds travel higher up the temperature trays inside the column, while the heavier ones stay lower. The crucial breakthrough in Dr. Chem's experiment is super clear when you look at the data. They took a batch of Eucalyptus globulus oil, which initially had an 84.63% concentration of eucalyptyl. That's the active compound responsible for that clearing scent you find in cough drops and bug repellents. After running it through that dynamic distillation column, Dr. Chem successfully isolated a main cut fraction, MC12, with an absolutely incredible 98.89% purity. But the experiment pushed things even further, tackling the highly complex eucalyptus citriodora oil. Even though this oil has over 11 competing components, the dynamic distillation model allowed the lab to hit a stunning 99.21% purity of isopulegol. This specific molecule is a hugely valued intermediate used for making blossom fragrances and menthols, all perfectly cleanly isolated. Next up, advanced molecular distillation. Protecting fragile molecules. We've just seen how vacuum distillation works, but what happens when the molecules are so incredibly fragile that even a lower temperature vacuum might burn them? Enter molecular distillation. This uses a wiped film short path unit, making it a strictly non-thermal process. The secret sauce here is the ultra-short path. We're talking sometimes just a few centimeters between the heated evaporator surface and the cooling condenser coil. Because there's a high vacuum applied, the molecules evaporate rapidly and travel that tiny distance instantly. They never suffer any thermal damage from prolonged heat exposure. Let's look at how this works in practice using orange essential oil as a case study. Orange oil is predominantly D-limonene, but the actual flavor and aroma come from a very tiny percentage of fragile, oxygenated compounds like linalool and decanol. Using molecular distillation at a very gentle 30 to 35 degrees Celsius, engineers can perfectly separate the bulk D-limonene into a light fraction. This safely captures that delicate flavor profile in the heavy fraction without burning a single thing. And our final step, mapping the chemical fingerprint, proving the purity. To wrap up the life cycle, we have to analytically prove exactly what molecules are sitting in our purified test tube. We have to map the chemistry. Let's break down how a gas chromatography mass spectrometry, or GCMS machine, does this in 4 elegant steps. First, vaporization. A tiny drop of the oil is injected and flashed into a gas. Second, separation. The gas is pushed by an inert carrier gas through a long microscopic coil. The highly volatile molecules race ahead while less volatile ones drag behind. Third, fragmentation. As they exit the coil, these isolated molecules get blasted with an electron beam, shattering them into charged fragments. Finally, matching. The machine reads the specific mass of those fragments and compares them against known databases to identify the exact molecule. The scientific literature calls this readout a chemical fingerprint, and honestly, it hits the nail right on the head. Every single peak on the graph tells you exactly what molecule is present and in what precise percentage. This rigorous testing ensures the essential oil is 100% authentic, unadulterated, and totally safe for therapeutic use. It's the ultimate proof of purity. But wait, what about the heavier terpenoids that just don't vaporize easily? Well, for those, scientists use high-performance liquid chromatography, or HPLC. Instead of turning it into a gas, HPLC pushes liquid-solvent mixtures through a densely packed column. By carefully tuning what they call ternary linear gradients, which is really just flawlessly blending 3 different solvents over time, scientists can simultaneously map up to 22 complex components in heavier oils like cinnamon, caraway, and cardamom. It's a brilliant chemical workaround to get that exact same level of precise mapping. So we've journeyed all the way from a crushed leaf in the dirt to a verified 99% pure molecule in the lab. But I want to leave you with this final provocative thought. As our processing technology perfects our ability to isolate and map these pure molecules without destroying them, what undiscovered therapeutic benefits are still hiding in the discarded complex fractions of these ancient plants? There is still just so much chemistry left to explore. Thank you for joining me on this explainer journey today, and keep learning.